Okay, so welcome everyone to lecture 4 in AF 2024, Finite Element Methods in Analysis and Design. My name is Andreas Andersson. I'm also the coordinator of this course. I'm gonna give this lecture today on isoparametric elements. I advise you to, if you haven't done it already, to buy the book or borrow the book from a friend. And this lecture will cover a large part of chapter 6. So what I'm going to present here today is, in one sense, an overview of the concepts in chapter 6, but it's rather theoretical concepts, and some of those concepts are quite new. So I advise you to read in the book if you haven't really already done so, to understand in more depth how this concept works. And you will be needing this concepts both for solving parts of exercise A and potentially also for parts on the exam. So it's quite important that you understand these concepts. I also have the Zoom group chat open, so during this meeting you can write questions or anything that comes into your mind, and we can have a short break and discuss any of these topics throughout. So to start with, I will mute everyone here, except myself, obviously, and we will get started. So the outline of today's lecture, as I said, will be chapter 6 in the course book. I will start with a short recap from the previous lecture that Kostin gave on Monday, where he went through continuum plane stress and plane strain elements, specifically the Q4 bilinear elements. I will only show maybe 2 slides on that just to recap slightly. I suppose even those concepts from his lecture might be quite new to most of you. What he showed is valid for rectangular elements, and if you have any skewed elements, you need to transform the geometry, and that is the concepts of the isoparametric formulations in order for the element formulations to work. So this has many practical implications, which is used in, I would say, any commercial finite element program. Also, using commercial software, you may sometimes end up with warnings or error messages related to distorted elements or things like that. And in many cases, the theoretical background can be found in the isoparametric formulations. So not only is it important throughout this course, but also if you're actually going to be using commercial finite element packages to understand why these warnings or errors come up and how they can potentially influence the results of your analysis. I will illustrate this on a very simple example using a 3-noded bar element. This element doesn't itself has any real practical application of this isoparametric formulation, but it's more of a illustrative way of showing concepts. Throughout this lecture, I will also try to follow the notations in the book, and I also have quite a few images and equations taken directly from the book. So this is more to see as an introduction to chapter 6 in the book rather than covering in great detail all the aspects of it. I will then go on to the 4-noded plane elements and isoparametric formulation for that. Not in extreme detail either, because the mathematics get a little bit expanded, sort of. It's a little bit tedious to go through all the details. So I try to be more detailed on the 3-noded bar element, and then showing the similar concepts on the Q4 elements. What will be clear a little bit later during this lecture is the numerical integration that needs to be done, which is going to be done using Gauss quadrature. I'm not sure if Kostin mentioned anything about numerical integration during his previous lecture, but in any way, I will cover that today. I will show some of the concepts of higher order elements, such as the Q8 and Q9 plane elements. The concepts are somewhat the same, but they get increasingly more difficult or tedious to solve, I suppose. But they have some important features compared to the 4-noded elements. And in many practical situations where you use commercial softwares, you may be facing selecting between, say, 4-noded, 8-noded, or 9-noded elements. And then I believe it's important that you know the difference in between these elements and when you should use which element. And also something about what can potentially go wrong and how this element should be treated. Also, the choice of integration order is very important for the different elements. I will illustrate that with some examples. So when you do before you do more large-scale finite element analysis, at least in the beginning, when you're not so used to doing that in commercial softwares, it's preferable to make small-scale models. And often, if you can find a case where you can have an exact solution to compare with, then you can estimate accurately the quality of your model. So you may often be able to solve the system, but you may, if you use wrong type of elements or wrong type of integration order, end up with rather poor quality of the results. Sometimes the software will give you a warning, and sometimes it will slip through anyway. So that requires some skills of the person doing the analysis, which I try to go through a little bit today. That will also be partly covered in the next lectures also. I think lectures 6 or 7 possibly. And then the last part is stress calculation and extrapolation. So I will show how we calculate the stresses in the integration points, which we call the Gauss points, and then how we extrapolate those to the nodal points. So this is the outline for today. It may seem a little bit abstract at the moment, but I hope it becomes a little bit more clear. I think that we may have some time in the end of this lecture as well to go through some questions. So I will try to take it fairly slowly today, because I mean, the mathematics is not super difficult. You have probably gone through more difficult mathematics during your calculus courses, but I think the concepts and the applications are rather new to most of you. Personally, I think I learn best when I try to implement things, and I like writing scripts in MATLAB to solve different kind of problems. And that is also part of exercise A, to implement these concepts using scripts in MATLAB. And we have a set of MATLAB scripts which are called Planey 4E and 8E, which calculates the stiffness matrix for the Q4 and Q8 elements. And these are also for the isoperimetric formulations. They will work even for rectangular or non-rectangular elements. So if it's rectangular, it will be the same as the concepts that costing went through on Monday. Then we have two other MATLAB functions or scripts, Plany4S and Plany8S, which evaluate the stresses of these elements. So one is for assembling the matrices. Then you need to write your own code for assembling the structure and solving the system of equation. And then the other two are for post-processing to calculate the stresses based on the displacement field. I will show some template script for this in the end. And all of these four first scripts have been developed at Lund University in, I think, starting in the early 1980s within a finite element toolbox, which is specifically designed for teaching. So I think the scripts have not been changed since the 1990s or something like that. But I mean, the theories are the same anyway. And then I made two short scripts, top of 4-node and 8-node, which only generates the element topology for the cantilever beam that will be part of exercise A. So the experience from previous years in this course is that students typically struggle quite a lot with assembling the element topology, which is not really what we intend to learn here. It's just simple scripting stuff. So I've given you the code for that. So you can use this template code and then add on the parts with actually calculating the matrices, solving the system of equation, and then post-processing the results. There are no questions so far, so I will just continue. So a short recap from lecture 3. We here have an illustration of the 4-noded bilinear rectangular element denoted Q4. We have 4 nodal points, 1, 2, 3, 4 in that order, each having 2 degrees of freedom, U1, V1, U2, V2, and etc. We illustrate this by an element that has the dimensions 2a times 2b with the coordinate system in the center. And we formulate the shape functions. I will not go through how you obtain this, but this is the solution. Costing went through this in more detail on the last lecture. The concept of the shape function is that it interpolates any entities within the elements. So shape function 1 should have the value 1 at node number 1, and it should have the value 0 at the other nodal points. So if we put in minus a and minus b, we end up here. So minus a minus b, we end up having the value 1. And you can test this for the other nodes 2, 3, and 4 and realize that we end up with values 0. You can also illustrate this by plotting this shape functions, say in MATLAB or some other software, which I've done here. So minus a minus b is down here. So this is node number 1. So shape function 1 has value 1 and 0 in the other nodes. So we can see that this describes a linear interpolation within the element using these 4 shape functions. And if you would add up all these surfaces, it will all have the value 1. So that is the basis for a rectangular element. The shape functions are described using Lagrange interpolation formula, which I didn't give here. So the procedure is that we would like to calculate the strain displacement matrix B which is the derivative of the shape function. And we also need the constitutive matrix E, which is a 3x3 matrix for plane strain or plane stress problems. And then we obtain the stiffness matrix K. Well, the notation in the book is small k here for the local stiffness matrix of one element. So it's a double integration over x and y bounded by minus b to b and minus a to a by b transpose e times b, multiplying with a thickness for plane stress problems. And we can express the shape functions as these bilinear polynomials exactly. And we can have fairly easy and exact solution to this K matrix, given that we have this rectangular element. That is also part of exercise A, that you will evaluate one component of this stiffness matrix. Doing the full 8x8 is a little bit time consuming if you do it manually. If you try to evaluate this integral in, say, MathCAD or some program, it's likely to crash because it's a little bit time consuming. As a hint, you can actually do it using the symbolic toolbox in MATLAB to evaluate this whole matrix directly. But you are supposed to do it manually by hand just to get the feeling of it. When we have this K matrix, as usual throughout any given finite element analysis, we solve the system equation K times D equals the forces, solve it with respect to the displacement field usually. And then the stresses are obtained as an extension of Hooke's law, where we identify that the strains are the B matrix times the displacements, which is effectively the derivative of the shape functions multiplied with the displacement field. So everything here is fairly similar to, say, bar or beam elements, but in 2 dimensions. And further, the same concept is extended, say, to 3D solid elements, but then having a triple integral because you have another dimension to integrate over. But we will not go through 3D solid elements in this course. The concepts are pretty much the same, but just more comprehensive in evaluation. And one of the important aspects of this is, again, that this is only valid for rectangular shapes. So normally under rectangular shapes is the only way we can solve this in a closed form. But typically we have more complicated geometries. We may have a structure looking like the lower picture here, where clearly these elements are not rectangular shapes. We can have triangular elements, but here we choose to model it with rectangular elements. And then elements will be distorted in different ways, which will, well, firstly influence the accuracy of the solution, and then for each of the element we'll have different shapes, and this need to be treated with what we call the isoparametric formulation. And in essence, it enables quadratic and hexahedral elements to have non-rectangular shapes, such as illustrated in this picture. This is also taken from the book, so you see the figure references here if you want to go into the book and read in more details about it. This isoparametric formulation is applicable to most elements because all elements need to be non-rectangular in order to be useful in analysis. we are using coordinate transformation from the non-rectangular domain, as we see here, to a rectangular domain. So we use a concept of mapping the real domain to a rectangular domain, in which we can use somewhat similar concept as for what we have learned before from the rectangular elements. So we solve it in the mapped domain. So the global X and Y coordinate systems is now denoted Xi and Eta. The same shape functions are used both when we interpolate coordinates and displacements. Before we didn't need to interpolate the coordinates really, because it was in a rectangular domain. But here we need to have the interpolation function for describing the coordinates in an arbitrary geometric system. The word isoparametric means the same parameter. So we use the same parameter for interpolating displacements and coordinates. Something about compatibility. Compatibility is that we have a C0 compatibility over element boundaries. This means that we have a continuous displacement field, because we cannot really have any gap in the analysis. So everything is connected in between the nodal points, even over higher order elements and intermediate points. So the displacement field is continuous, but if you have C0 continuity, we may have a discontinuous strain field. So the strain or stresses may have gaps in between the elements, or not gaps, but rather discontinuities. This is often quite unrealistic because we would expect the stress field also to be continuous. But if you evaluate the stresses within adjacent elements, you find this gap. And one way of treating that is to extrapolate the stresses to the nodal points and then take an average value for each of the nodal points. So I will show that concept later on. And you will also need to use that in part of exercise A with the cantilever beam. Something about completeness means that we need to have arbitrary constant strain rates and arbitrary rigid body motions. I will illustrate this also with some examples of how elements can deform and how they are allowed to deform. So that's the concept. So basically, isoparametric formulation is a way of transforming non-rectangular elements into a rectangular domain in order to be able to first describe or evaluate the stiffness matrix, and then later on to evaluate stresses for our application. And we go from a global domain XY to a mapped domain Xi Eta. Okay, so I have a question here. Can you go back one slide and explain how you wanted us to do with a K-matrix 8x8? Can you explain a bit more what you want with that? So Pierre, you can unmute yourself if you want, if you have any questions. Let's see if I find Pierre. I will try to unmute. It didn't work so well. So the 8x8 K-matrix. Sorry, Pierre, I cannot unmute you for some reason. I don't know why. Anyway, Okay. Well, you cannot really solve it in MathCAD. If you try, at least one time when I did it, it will crash. No, you only need to evaluate one component. So if it's component row 6, column 5, or something like that, you only need to find those rows and columns and sum up the contribution to that. So you don't need to sit down manually and actually solve the full 8x8 matrix, because it will be a little bit time consuming. So I hope that answers your questions. Okay, so I will continue. Great. Okay, so now we will illustrate this on a 3-noded bar element. I know that Costin also had an illustration of the 3-noded bar element when illustrating consistent nodal loads, and also when evaluating stiffness matrices. I would say that the 3-noded bar element, well, sometimes called a cable element, is not used very often, but it's good for illustration anyway. So we have a physical element here going from node 1 to 3 with an intermediate node 2. We have a coordinate system starting somewhere off to the left in the x direction. So in a general way, we have the coordinates nodes at the coordinate x1, x2, and x3. And the element has a length L. And this somewhat unsymmetric element, we would like to map it to using the isoparametric formulation to this domain, where we start with a coordinate c in the center of the element, and it has a length of 2 units, so from -1 to +1. And I will illustrate how we do this mapping from the physical domain to the map domain. The shape function, Costin also illustrated that, I believe, in the last lecture. Here we use the notations in the map domain. So instead of x, we have c. So this is a second-order polynomial shape function having value 1, 0, and 0 in the other nodes. And this also second-order function 1 here and 0 in other points, and so on. So in a structured way, we will write the shape functions in this format. So this is the shape function vector. And what we would like to do is calculate the stiffness matrix for this local element using the same approach, the integral of B transpose E times B. We know that the B matrix is the derivative of the shape functions. The thing is now that the shape functions is a function of xi rather than the global coordinates x. And here is where it gets a little bit non-intuitively, perhaps. We know that the strain is the derivative of the displacement fields. So we would like to calculate the derivative of the real displacement fields, which is in the real domain, the u dx, giving displacements u along this physical element. But we cannot really do that directly because the shape function is instead a function of the mapped coordinates c. So we can describe this as the derivative ddx of n times this displacements, where ddx is a derivative which involves both x and c. So dx dx d dx. So this is the fundamental that we need to derive the function, calculate the derivatives in the map domain. with respect to the global domain. Once you have done all this procedure, the concept is similar for other more complicated elements. So I will try to go through this a little bit slowly. So please do text some questions if you have it. So effectively, what we would like to do is calculate this derivatives, ddx. But what we will start doing is that we will calculate the inverse of it, dx dxc instead, which can be described like this. So we derive the shape functions with respect to the mapped domain C. So we derive this one, and then we have -1 and 2c. We have minus 2c, and then here half and 1 plus 2c. So we differentiate this with respect to c, ddc of n, times the physical coordinates x1, x2, x3. So this is dx dxc that we have calculated in this way. But if you look here, we are not looking for dx dxc, we are rather looking for dxc dx. So actually we are looking for the inverse of this expression. So we take the inverse, we call this J, which is denoted as the Jacobian. And the Jacobian is a matrix of first order derivatives, which is just a general mathematical tool, if you like, which is illustrated here. So this is the first derivative of this function, n. We take the inverse of all this. Just for short, we denoted j here. So we have 1 over j, which gives us dxc dx, which is this first part. But then on top of that, we still need to do again d dxc, which is just to derive this expression once again. So we have 1 over j being the inverse of this expression, and then the derivative of the shape function again. So again, 1 is -1 plus 2c, and etc. So already here, this is a rather lengthy expression, but it's a function both of the mapped coordinates c and the global coordinates x1, x2, x3. So far so good. We have then calculated the B matrix using these derivatives. So this is the key to the problem. See, go to the next slide. So finally, when we have the B matrix expressed in terms of both mapped and global coordinates, we need to calculate B transpose E times B. In this case, E, the Young's modulus, is just a constant, and the cross-sectional area is, in most cases, also constant. Integrate this over the whole element. So this is the general procedure, actually, when you have the B matrix in only global domain. But now we have it formulated in the map domain. So instead of integrating from the whole element length, we integrate from -1 to +1 using the newly obtained expressions for B. And you can break out the Jacobian here. If you go back here, so the B matrix is described like this. So, I mean, the physically speaking, or practically speaking, the Jacobian can be seen as a scale factor that maps the physical domain here to our mapped domain over here. And the Jacobian is usually a function of Xi, and it cannot be integrated directly in closed form. I mean, for simple cases, it can, as we can see here for the three-node bar element. But if you go to more complicated elements, we typically cannot generally integrate it in closed form. And for that reason, we need to use some numerical integration scheme to evaluate this integral. So I will come to that in a while. Using the Gauss quadrature, which is usually the most accurate and efficient way of evaluating these kind of integrals. So I hope that everyone follows the concept so far, because this is the basic concepts of the isoparametric formulation. Okay, great. So in order to further understand this, we make an example with the same three-noded bar element. So we had it. Okay, so question: how do we know the shape factor or shape function is second-order polynomial? For a two-noded bar element, it would be a linear function, but we need to find a function that has the value 1 at the point that we are expressing it in. So the shape function at node 1 need to be 1 here, and 0 in the other positions. And for having a C0 element, we need to have a continuous displacement field. So we cannot have any kinks in that. So I believe that, yeah, okay, it could be a higher order, I suppose, but you would strive after having the simplest function that can satisfy the condition that it has value 1 at this node point and 0 at the other points. So if you have higher order functions, you are likely to end up with some spurious displacement field in between there. Also, if you use the Lagrange approach in determining this, you will end up having this. I don't think there will be a denominator singularity problem when we integrate this system. I mean, it could be if the nodal points are positioned in a very awkward way. So typically, if you have, say, if node number 2 would be outside of the element or not bounded in between node 1 and 3, then you will have a singularity. And this will end up in the form that your Jacobian or the determinant of the Jacobian cannot be evaluated. So I will give some examples in that in the end when that happens. This is maybe more the risk for 2D and 3D elements, where you can come up with a very distorted elements where the integration points are outside of the elements or in awkward positions of the elements. Okay, so back to this example, and just for simplicity, we have this example as we put a node in the center point. So Costin solved this problem in the previous lecture using the energy approach. And we will see here that we will end up with the same result using the isoparametric formulation. So going through quickly here, we had from the previous slides the shape function. So we assume the same shape functions, obviously. We differentiate that with respect to the coordinate xi. So we have dx xi like this times the physical coordinates from minus L/2 to plus L/2. So this is the same as we were doing here to evaluate the Jacobian. But if we rearrange a little bit, we will end up that this has a constant value of L/2. And then the B matrix, or rather vector here, is the inverse of that times the derivative again, d dx. So we have the inverse of L/2 is 2 over L times the derivative of n with respect to xi. So this expression again. So this is a fairly simple expression, only as a function of xi and the physical coordinate L, or geometry L rather. We calculate B transpose B, because this is what we need for the K matrix. And it takes the form of this expression. Not going through, it's just simple mathematics to multiply each component there. So we can break out 1 over L square and end up with this expression. And E and A are constant values. We can put those outside of the integral. And then we just evaluate this integral over the range from -1 to +1. I'm not going to go through the integration, but obviously you can integrate all these components fairly easy as the integral with respect to the parameter xi. And when you rearrange this a little bit, you will end up an expression looking like this: EA over 3L, and this 3×3 matrix, 7 minus 8, 1, minus 8, 16, 8, minus 8, sorry, 1, minus 8, and 7. And if you go back to lecture 3, you will see that this is the exact expression. Sorry, I should say lecture 3, not lecture 2, I believe. Or maybe it was lecture 2. Anyhow, from the previous lecture of Costin, this is the exact same results. So I think that we can take a 15-minute break here, and then after that I will continue with similar formulations for the Q4 elements. Okay, let's see. Okay, so let's get back to the lecture. Full screen mode, hope you can see it. So we have now gone through the isoparametric formulation and illustrated that on 3-noded bar elements. This covers like 3 pages in the book, so I intentionally made it relatively slowly. I hope you could follow the concepts. The principle is pretty much the same with the other kind of elements, which I will now show for the Q4 elements. So I will try to speed it up a little bit, but still, if you have questions, write something on the group chat. So here for the Q4 element, xi, and we now define another variable or coordinate eta in the perpendicular direction, since it's obviously a 2-dimensional element. And xi and eta need not be orthogonal or parallel with the Cartesian coordinates x and y. So we have the xy coordinates, and we have the map system xi eta, which starts at the element center. but this is not necessarily the centroid of the element because it may have a skewed form like this. And again, when we go from the physical domain, which we illustrate here, to the mapped domain, it has 2 by 2 units of dimensions. So similar again, we want to go from the physical domain to the mapped domain. We use the same shape functions for the geometry and for the displacements. And that's why it's called isoparametric, that we use the same order of shape functions for both of them. You also have other concepts called subparametric or superparametric, but I'm not so sure if that has any relevant application, not here anyway. And our aim is to calculate the K-matrix using the similar principle as for the 3-noded bar elements. But now we need to consider the 2 dimensions instead of only 1. And we need to write this in a fairly compact way, which also follows the notations in the book. So we have an assembly of the coordinates for each of the 4 node points, x1, y1, x2, y2, and etc. We would like to describe this using the interpolation functions or the shape functions at any given position within the elements. So the general coordinates at any given point in the structure can be described as a summation of the contribution from each of the shape function. So you have any given point here in the structure, you need to multiply shape function 1 with that specific coordinate and do the same throughout the whole element. In short, this is written n times c, where c is the coordinate vector. And we do the same concept for the displacement field. So we have the coordinates c and the displacement d, which are described by these vectors, x1, y1, etc., u1, v1, u2, v2, etc. And as was shown in previous lecture, the shape function matrix, which is now a matrix, can be arranged in the following way. So this is just matrix algebra. And the shape functions are also, as I described from the first slide, bilinear functions in the xi-eta domain, like so. So the first step now is that we would like to calculate the B matrix, the strain displacement matrix. And now in 2-dimension, it involves gradients. So let us define a function phi, which is a function of the mapped coordinates xi and eta. And the derivative of phi with respect to xi can be described as the phi dx, dx xi, the phi dy, the y dx xi. So this is also basic calculus. And we do the same in the eta direction. So it's a partial derivative involving the global coordinates x and y and the mapped coordinates xi and eta. In a more condensed format, we write phi prim xi, phi prim eta, which is the Jacobian matrix times the derivative in the global domain. So here we see again the Jacobian matrix is the mapping from this domain to the from the map domain to the global domain. And by definition, the Jacobian is a matrix of first order partial derivatives of a vector valued function, which can be written like this. So differentiate with respect to x with respect to xi, y with respect to xi, and the same with eta, which can be written as a summation of the shape functions, or the derivative of the shape functions times its coordinates, in a similar way that we did with three-noded bar element. So if we differentiate the shape functions following this scheme, here we have the shape functions, we will end up having this expression times the physical coordinates, which we now denote the Jacobian, which will be a 2x2 matrix having the elements J11, J12, J21, and J22. But as we realize from the bar element, similar here, we need to calculate the inverse of the Jacobian rather than Jacobian itself. So we denote the inverse of the Jacobian by capital gamma, which is defined as this, where J is the determinant of the Jacobian matrix. This is also just basic linear algebra. So we have determined all these components, 11, 12, 21, and 22, out of this matrices. So then we can just operate on those in order to determine the inverse of this Jacobian. And again, the Jacobian is a scale factor going from the local domain to the global domain. And physically, the Jacobian is the area divided by 4 if the element is either rectangular or a parallelogram, looking something like this. And for other geometries, the Jacobian has other values. So this is the basic concept. It's written in a relatively condensed form because if you expand it, it gets a little bit messy. So what we would like to do is further to calculate the B matrix. Obviously, we now have the Jacobian. We can also recall that in 2D plane stress or plane strain, the strain in the x direction is the derivative of the displacement in that direction. Similar in the y direction, and then we also have the shear strains as a derivative of the y and the uy and v with respect to x. And this can be rearranged in matrix formats like this. So we have epsilon x, which is u prime x, epsilon y being b prime y over there, and then the combination gamma xy as a combination of u prime y and v prime x. And if you use the previous expression for the inverse of the Jacobian, the 2x2 gamma matrix, we can expand this in terms of the coordinates u and v, which is derivatives of x and y, which we will be using for the strains here. So expanded format of this one will look like this 4x4 matrix. times the vector of the displacement in the local coordinate system. And then we have the shape function times the displacement, and the B matrix is the derivative of this expression, which in expanded format looks like this. So it has a great similarity with the regular rectangular four-noded elements, but instead we have the map coordinates xi and eta here. So this is an 8x4, 8x4 matrix, and times the 8x1 displacements. So now we actually have all the components in order to assemble the stiffness matrix. So the B matrix will be a 8x3 matrix. E being the constitutive matrix is 3x3 for plane strain or plane stress. We multiply with the thickness in the case of plane stress. And in global domain, we differentiate, or we integrate, over the global domain, dx dy. But now instead we have the mapped domain, which we integrate from -1 to +1 in the two directions. And we have the Jacobian here that we have also defined. In case you will have a variable thickness over the element, you can use the shape function to interpolate that as well. But for most application, I would say that you have a constant thickness. So it seems that we have a well-defined closed form expression for this one. But when inspecting these components in more detail, it's difficult to evaluate this in a closed form in this xi eta domain. So for that purpose, we will resign to numerical integration of this double integral, or in 3D elements is a triple integral, at least for solid elements. So now I'm going to talk a little bit about the numerical integration scheme, and the most common one is the Gauss quadrature, which is just a method of numerical integration. It's kind of slightly different compared to, say, the trapezoidal rule, because it gives much better accuracy for higher order polynomials. So we define a sample function, or sample of function phi, illustrated here. So we would like to integrate phi by using specific sample points and multiplying those with a weighting factor. So we have a problem having a closed form integral of this expression phi, generally speaking. And the sample points, I will not go through in detail how you determine those. So for now, you can accept that they are at certain locations, but they happen to be roots of a so-called Legrand polynomials. But that's outside of the scope of what we're looking at here. So just accept that you will have the best solution at these specific points. And this says that a polynomial of degree 2n minus 1, being this sample function phi, will be integrated exactly by n points of this Gauss quadrature, which is good news when we would like to have accurate results in our analysis. So we integrate from -1 to +1. So in the first case, we have one sample point here, the solid rectangular box here, which is the Gauss points. So we evaluate the function at this point, call it phi1, and the integral is simply the area, the gray shaded area, so 2 times phi1, because we go from -1 to +1. Similarly, if we have a 2-point Gauss quadrature, we have two sample points located at distance a from the center, where a happens to be 1 over the square root of 3. And since this goes from 0 to -1, it's 1 times phi1 plus 1 times phi2 being the integral value. And for a third order Gauss quadrature, we have the distance b being the square root of 0.6. And then the weighting factors are as follows here. So this will give the best result of the integral. So this is just conceptually showing the principle of the Gauss quadrature in one dimension. But the same applies in 2 or 3 dimensions as well. So the weighting factors W times the value of this sample function at certain locations. So if you look in 2D, we have a sample function that is now a function of xi and eta. And we can use the going from the integral solution like this, we can use the product rule to end up with a summation, which means that we are just summing up the values at this sample function at specific locations, multiplying those with the weighting factors, and the result will be the integral value. So if you have a 1-point rule, we have the integration point in the very center of the element. We call it phi1. And then it's just the element size is 2 by 2 units times this value phi1. And now we have, if you have a 2 by 2 integration, we call it a 4-point rule. And here the numbering of the Gauss points is 1, 2, 3, 4, like so. In the MATLAB code that I will illustrate later, we have a different notation, I believe, which needs to be accounted for in order to keep track of which Gauss point you are evaluating. So here you just evaluate the sample function at this specific locations, and the integral value is just the sum of those. And for the 3 by 3 order Gauss quadrature, it's similar, but with other factors like this. So this is this principle of solving this integral by a numerical approach rather than in a closed form. And we need to do this for each of the elements of our system. And typical for many structures in, say, civil engineering applications or mechanical engineering or whatever, you may end up having tens of thousands or hundreds of thousands of elements. And generally, each of these elements are likely to have different irregular shapes and need to be evaluated individually. So it's a matrix multiplication of this B transpose EB for every sampling point in every element. But this could be reduced due to that we have a symmetry in the K matrix. It's typically very narrow banded, that you don't have any strong correlation between, say, node point 1 and node point 4. So it's a very diagonal matrix. So the procedure will be effectively in this 2-dimensional element, 2 main loops, where you loop over the integration points in the xi direction and in the eta direction. So if you have a 2 by 2 integration rule, Ni and Nj is 2. So for each of the element, you calculate the B matrix, have a thickness that may vary, and evaluate the Jacobian at the specific point. you calculate B transpose E times B, inclusion of the Jacobian and these weighting factors, which will be the integral value of the stiffness matrix at that specific point. And you add that contribution to the local K matrix. So for a noded plane element, we have the 8x8 matrix. We start with the first sampling point or Gauss point. We evaluate this expression and add that contribution in the matrix. And then we continue with the second, third, and fourth Gauss point. So for each element, we need to evaluate this in a loop 4 times and do that for as many elements as we have in the structure generally. So this seems a little bit time consuming, but typically it takes very short time in most commercial softwares, owing to that this Gauss quadrature method is relatively or very efficient. So that's the general concept of the Gauss quadrature to obtain the stiffness matrix. The same applies for higher order elements. I'll not go into detail about it because there's not so much different about it. It's just that the mathematics get a little bit more extensive. Instead, I would like to talk a little bit about the different pros and cons with different elements and what you can expect from those, still in the framework of plane elements. So if you talk about higher order elements, and we now restrict ourselves to the 8 or 9 node elements. The 8 node elements is sometimes called the serendipity element, and the Q9 for the Lagrange element. And they allow for curved sides since they have higher order shape functions. So it's easier, firstly, to fit these elements to an arbitrary geometry. And also they have improved performance under bending-like problems, which I will illustrate with some examples. If you go to the Q8 element, it can actually exactly represent the state of pure bending if the element is rectangular. For non-rectangular elements, it has some significant deficiencies. The Q9 element can represent state of pure bending even for non-rectangular, but if it's straight-sided elements like parallelograms. And it's generally less sensitive than the Q8 to non-rectangularity. So for general unsymmetric elements, the Q9 may be preferable. This table is also taken from the book illustrating the shape functions for the Q8 or Q9, or you can have a mixed formulation with other number of nodes as well. So you have the first 4 shape functions, which is just the bilinear functions, and then you have second order polynomials in each of the xi and eta direction, which are represented by each of the side of the element. So it will have a second order polynomial along one direction here, and then linear in the other direction. And doing so for the 4 different sides. And then in case of the 9 node element, you have a polynomial in the 2 directions. So it will be sometimes that it's called a bubble function. So this is just how these are assembled. So when you have, say, a 9 noded element, I is equal to 9, and then you need to add this contribution to the lower order shape functions as well, for reasons of completeness and compatibility. So again, this could be plotted easily, say in MATLAB or other softwares. So we have from before the 4 bilinear shape functions, now slightly modified with respect to the higher order elements. So we have this components. So shape function 1 is also including shape function 5 and 8 in different components. Sorry, it's only number 9 here if I equals 9. We have the outer set n5 to n8 being, as I said, the second order polynomial in one direction and linear in the other direction for equally of the four sides. And then we have finally this bubble function. So that's the illustration of this shape function for Q9 elements. I'll come back to some applications of these elements. But first, something about the integration order. So we talk about full integration and reduced integration, and these are important aspects of the elements. So the full integration is a quadrature rule that exactly integrates all the stiffness coefficients of an undistorted element. So if you have a rectangular element, and due to the principle of the Gauss quadrature, you will have the exact same result as if you solve the integral exactly. The Jacobian of an undistorted element is constant within the element. And typically for, as I explained before, for Q4 element, it's L over 4. For a Q4 element, a 2x2 Gauss quadrature is considered full integration. And for a Q8 and Q9, a 3x3 quadrature is full integration. A reduced integration order is any quadrature that is less than full order, basically. This may improve the accuracy of the elements by offsetting overstiff behavior, avoiding, you may also have softening due to that some polynomial terms vanish at lower order rule. But you also have a risk of introducing defects as spurious modes or severe deficiencies of the elements. So the minimum quadrature rule is 1 point for the Q4 and 2x2 for a Q9 element. That's the minimum that you need in order to be able to evaluate the K-matrix. So if you look again at the Q4 element, we can have these different states of displacement modes. So the first 3 modes here are just rigid body modes. So the relative distance between the nodes are unchanged. So we don't have any change in the relative displacement and hence no change in the strain. So we have a no strain energy. So these are just rigid body modes. They will move in a rigid sense, either translation or rotation. And then mode number 4 to 6 is constant strain modes, either expansion or deformation in a symmetric sense like so. And then we have mode number 7 and 8, which are bending modes. So we induce bending in the elements. Now, if we have reduced integration, we don't have any strain for mode 7 and 8 because it's evaluated in the center point. And this may be important for reducing, say, shear locking effects, because you will not have any contribution from bending. And if you try to bend this element, it will become over stiff because you only have linear sides. So that's one trick to reduce shear locking effects. But if you look at one example here, we have a cantilever beam length L times H. And this is also taken from the book, and it's subjected to a horizontal point load P at the center node here at the tip. And the values are chosen such that the theoretical displacement along the axial direction is equal to 1. And if we solve this, you can do that with a MATLAB script actually, or in other softwares. If you have a 1-point Gauss quadrature, we will not be able to resist any bending in the system. So the system will deform in a very unnatural way. So the bending stiffness component doesn't exist because we cannot activate mode 7 and 8. And therefore the deformation in this particular system will be severely distorted. And we have a displacement that is 37 instead of 1. If instead use a 4-point quadrature rule, 2 by 2 points, we have a displacement that is overestimated by some 10%. So it's way much better than this reduced integration in this specific case. If you continue with the stress calculation in these Gauss points, as an extension of the Hooke's law, we have that the stresses is just E times epsilon. So the Young's modulus times the strain, but in 2D plane stress, we have the constitutive matrix E. And our strains can be described by the strain displacement matrix. So we have already the B matrix, and we multiply with the local displacement field of each element. So it's important that we have the local displacement of these elements. And we evaluate the stresses at the Gauss points, which are inside of the elements, which is the most accurate description because our integral is most exact at these Gauss points. And then we use the same shape functions as we have described before to extrapolate whatever stresses we have in the Gauss points to the nodal points, because typically we are more interested in the displacement along the boundaries of the elements, because in many applications you will have higher stresses and more relevant results over there. As I mentioned in the very beginning of this lecture, is that we have a C0 continuity, which means that we have a continuous displacement field, but we may have a discontinuous strain field, since the strain is the derivative of the displacement, which means that if we would add another element on side of this one, we will have a continuous displacement within the elements. So the displacement at this intersecting node will be the same, but the evaluated stresses may not be the same coming from different elements. So you extrapolate the stresses to nodal point A, and then corresponding from the intersecting element or adjacent element. And they may have different values, most likely. And one sort of compromise to come across this is to use an averaging. So you take the average value from the intersecting elements, and that's sort of the best estimate of the actual stress at that location. This could also be used as a quality measure for your solution. So the more you refine your element mesh, the less discontinuous stress field you will have. You will still have a discontinuous stress field, but the differences will be smaller and smaller. So that can also be used as a quality measure. So a little bit more in detail on how this extrapolation goes is that we define a coordinate system RS here, which is proportional to the Xiata system. So both in the mapped domain. And say here at the point number 3, we have this RS system is coordinated 1, 1. And the corresponding coordinates in the Xiata system is using a 2x2 quadrature rule, 1 over the square root of 3. So then we can express R as a function of C, like this. And we define the shape functions in a similar format as we have before, but now as functions of the RS coordinate system, which is mapped to the integration point. And then we use those to extrapolate to the nodal points. So the shape function, the stresses at any given point R and S in this domain is a linear combination of the shape functions defined at point A, B, C, and D. And this can be rearranged into a matrix form, the stress matrix, which is for a 4-noded element, plane element is a 4x4 matrix having this format. So it only contains 3 components, which are given here as G1, G2, and G3. So the sort of Gauss component 1, 2, and 3. And the same applies for different stress components. So in plane stress applications or plane strain, you have 3 components. You have 2 longitudinal and axial stresses, sigma x and sigma y, and then you have the shear stresses. And the SM matrix is given in the MATLAB code because that element formulation that was originally developed by Lund has a different notation than what is given here. So I have rearranged those components a little bit. But again, this is a measure of, or a method of extrapolating the stresses from the internal Gauss points 1, 2, 3, 4 onto the nodal points denoted A, B, C, D. Yes, I think that we can take, say that we take a 15-minute break here. So we reassemble at 10 past instead, and then I will continue with the lecture there. I will still be available here if you have any questions. Okay, so I think we can start again and continue the lecture. So I just went through the stress calculation procedure. So for the last part of this lecture, I will go through some examples of different elements and potential problems with different elements. And in the end, also show some small samples of the MATLAB scripts that you will be using for the exercise. Here's another example of a cantilever beam. It's a rather common example because it's a fairly simple system, but it could be good to illustrate the efficiency of different elements. And to the left, we have Q8 elements, so second order elements. Actually, it's also solved by Q9 elements, which have a nodal point in the center. And we have a cantilever beam here, which the numbers have in the book been adjusted so that the vertical displacement V at point C is theoretically 1. And then they explore. I just taken these numbers directly from the book, so I didn't actually work these numbers myself. They compared different element formulations and different Gauss quadratures. So we have the 2x2 and 3x3 quadrature. 3x3 being the full integration and 2x2 being the reduced integration. And if you look at the first one, where we have two rectangular elements, but they are elongated like such, we have fairly good results for all solutions. The Q9 with reduced integration is actually the best one in this case. But if you go for the second example here with just shifting the mid node of the elements here slightly, we severely distort or severely disimprove the results for all of the Q8 elements. So because we have I suppose bending components coming into play here, which severely distorts the elements, which could be described better with a Q9 element and reduced integration. So generally you have less accurate results for distorted elements if you have elongation or non-rectangularity as we have here. Side curvature or off-centering of side nodes. So even if these nodes will be moved or shifted, you will also have larger inaccuracies. And for the last example, when we have shifted the midline like this, we also had very poor results for everything but the reduced integration using Q9 elements. The obvious remedy for improving the quality would be to have more elements. For this symmetric structure, it's not any reason for having anything else but rectangular elements. But if you have a typical general geometries, you need to have some curved or deformed elements. And you need to improve the number of elements until you have sufficient accuracy in the results. I would say that it's mostly for very simple cases that you have an analytical solution to the problem. But still you can make some convergence check by gradually increasing the number of elements and see if there is any difference in that solution compared to the previous solution. If you have two distorted elements for any reason, many commercial software will give you a warning message that the mesh is too distorted. So they have trigger values on how much an element can be distorted in order to be accepted. Sometimes you may still accept to have some distorted elements, because if you would like to improve the solution not to have it, maybe you will have too many elements and it will not be computationally efficient. So it's kind of a trade-off between having good enough accuracy of your solution and having a efficient analysis. If you're only solving one system once, then it might not be a problem that it takes a bit longer time. But if you are, say, doing a large parametric studies or solving for a large number of increments, say like in dynamics or nonlinear analysis, then having a large system of equation may significantly slow down the computation of the whole system. So that's a little bit about the accuracy of the results. And another illustration of the Q4 element with the same cantilever beam, having other kind of distortions. So here we have perfect rectangular elements. Still with 5 elements, you only get about 70% of the theoretical results. Whereas if you have 2 elements using second order elements, you have very accurate results. So if you compare this one with this one, the Q9 is much more efficient. If you induce some distortion, say of this element here, you will have an even worse result. And if you would like to improve your solution by increasing the number of elements, you also need to consider that it's not always good to improve the mesh density or the number of elements in one direction, because each of these elements will still be elongated, so not so very efficient. So still, if you have, I don't know how many elements I have here, 10 or something like that, we still only have 86% of the real solution. So a better trade-off would be to have, say, the 5 element solution and just split it in half, like so, maybe, to have as symmetric elements as possible. What also may happen if you have distorted elements is that if it's too distorted, the Gauss points or the integration points may lie outside of the elements. Mathematically, this means that the Jacobian has a negative value, and you will have problems solving the system of equation. If 2 nodes of an element overlap, then the Jacobian will be 0 at that specific point. So the Jacobian is evaluated at all the Gauss points. At that specific point, you will have a 0 value of the Jacobian. So 0 contribution to the integral in that specific point. So for well-shaped elements, the Jacobian does not change much. The value of the Jacobian doesn't change much within the element. And badly shaped elements surrounded by well-shaped elements are expected to mainly influence the results locally, which means that if you have one distorted elements in the global system, you may expect to have poor results within that specific element. But unless that specific part of the structure is very important to the global behavior, that will mainly influence the local response. But I mean, if you go back to this example, if this element here, which is possibly crucial to represent the global stiffness of this whole structure, because everything is taken by this element here at the clamped part, then this element is very crucial that this element is well described. If you put this distortion out in the tip here, it's likely to have less influence on the results. But this is difficult to assess in a general structure, I suppose. But as a rule of thumb, it only influences the stiffness contribution for that specific element. So yeah, actually now we come to the part of the MATLAB scripts, which are available on Canvas. I don't know if you have had time to look on it. I can also open MATLAB and show it a little bit if you like. So we have these 4 functions, Plany4e and Plany8e, which are used for calculating the K-matrix for the Q4 and Q8 elements. And then we have the corresponding code for evaluating the stresses. And then we have the basic script that you will be using for solving the plane stress cantilever beam problem in exercise A, in which I have already structured the topology for the system. So it follows the following convention. So for a 4-noded element, you have node number 1, 2, 3, and 4 as such. And then the integration points denoted row-wise from the bottom, 1, 2, 3, and 4. And this differs from the notation in the book. And then for the 8-noded element, node number 5 is located in between the first edge, in between node 1 and 2. and then the same 6, 7, and 8. And the definition of the stress components, you have your sigma x, sigma y, and the shear stress is sigma xy. So you will have, for each of the Gauss point, you will have 3 stress components. So when you run Plany4S, the output will be the stresses at the Gauss points. So 3 stress components for each of the Gauss points. And then you would need to use this extrapolation stress matrix to go for each of the Gauss point and each of the components, extrapolate from the nodal point, from the Gauss points to the nodal points. And this, I only provided that for the 4 nodal element, and as I recall, I don't require you to calculate the stresses at the node points for the 8 nodal elements. So I believe you only need it for the 4 nodal one. So looking through, this is just a command for the Plany4E function. So your output will be the local stiffness matrix for the specific element. I mean, in the example of the cantilever beam, all elements are rectangular, so you don't actually need the isoperimetric formulation for this specific case, but it's included in the coder anyway, so you need to understand how that works. The element coordinates are assembled in a vector EX, which is just 1, 2, 3, 4, and similar for the EY, second command. And the third command is the element properties, in which p-type is just a switch, which is 1 for plane stress, which you will be using. T is the thickness, and ER is the integration rule. So for a 2x2 Gauss quadrature, in this specific script, ER is defined as 2. So you have 1, the thickness, and then 2 for full integration of a 4Q4 elements. And then I'm not sure if you need the constitutive matrix as inputs. Oh yeah, of course you do. Sorry. So what is denoted here, D, is what you are used to have as E, the constitutive matrix. So that's need to be defined as well. So for plane stress, it's described like this as a function of the Poisson's ratio. And this will give you the K matrix, and after that you need to assemble the component of the stiffness matrix to the different elements and apply the boundary conditions, apply the loads, and solve for the global displacements. And when you have the global displacements, you will use this function Plany4S to calculate the stresses. And the input again is the same coordinates, EX and EY, the same properties, EP, and the same constitutive matrix that you have already defined. And also the input will be the element displacement vector. So you need to define all the displacements in one row for each element. And your output will be essentially the element stresses and element strains, whereas you are interested in the element stresses, ES. This is written in a general format, both for plane strain or plane stress, but you will have the sigma x, sigma y, and tau xy as your output. And this output you need to rearrange for each of the elements, extrapolate those to the nodal points, and then average for adjacent nodes. So this is the cantilever beam from your exercise. This illustrated the formation using, in this case, Q8 elements, 10 by 2 elements. And I will show the element topology, but it follows a convention that you start from the lower left corner. This is element 1, 2, 3, and etc. Until it reaches the end, and then it starts on the second row. So here's element 10, element 11, 12, and so on. And the only input you need is the geometry and the number of elements in the two directions. So this is the example of top of 4 node for the 4 noded elements. So you input the length, the height, number of elements along the length of the beam and along the height of the beam. And this is just a plot factor to scale the displacements of the final plot. So you can start using this script, and then here you will add your specific code for calculating the K-matrix. You may also realize that for this geometry, all the elements are the same, so you only need to calculate this once. And then all elements, the stiffness matrix of all the elements will be the same. So you do that once, and then you assemble that to a global matrix. So here your instruction code related to the degrees of freedom, fixed degrees of freedom, and so on. So when you apply your boundary conditions. And this generates the EDOF matrix, which is the element topology, using this relatively compact code for the number of elements. Yeah, sorry. So in this code, you calculate the local K-matrix, and down here, after you have the element topology, obviously, you can use that in order to assemble the global K-matrix. And then you need to make some code that assembles the global load vector for this distributed load along the line here. You solve for displacements, and also you need to calculate direction forces, which was given, I think, in the same principle as in lecture 1. So you will have some reaction forces along this clamped edge here, and you would like to express those in terms of vertical forces and bending moments. So you just need to add up the components and see what the resulting bending moments is. Because plane elements only have translational degrees of freedom, so you don't have any rotation and bending. But you will have a set of horizontal reaction forces, which can be defined as a bending moment along the center of the section. And here is this stress matrix for extrapolating the stresses from the Gauss point to the nodes. And this has been rearranged to follow the convention of this figure, which is used in the scripts. Yeah, and then in the end, this is just a simple part of the script to make this plot here. So you don't need to consider about that either. Just it's made automatically. And it's also good to make this plot to make sure that everything is, that the displacement field is continuous, so nothing looks too strange, because then you have likely assembled the system in a wrong way. So that's actually all of the presentation for today. Let's see if this makes any sense of using MATLAB here. So I have all these functions. I don't think we need to go into detail about all the details of the code. Here it calculates the determinant of the Jacobian and stuff like that. So you can look through the codes of the Planifor-E and Planifor-S to get familiar with the concepts. And then use this topology scripts. So if I run this one, it produces this plot of, in this case, the undeformed geometry. And if I type EDOF here, you will have the element topology. So the first element connects these nodal points. So that's the basic structure for all of this. So let's go back to the slides here. Yeah, so now I think we have some time if there's anyone who would like to ask questions.
I have questions to ask.
Great.
Yes, it's in page 12.
Okay.
And
yeah.
Yeah, in the second line it says the function phi must be multiplied with a weighting factor. So how can we determine those weighting factors?
Let's see if I'm on the right slide. Can you see my desktop now, or did I stop sharing? Can you see it?
Sorry, wait for a minute. You need to go
sorry,
down.
Yeah.
Maybe we have different page numbers. You have to go down.
Yeah, it's in the numerical integration.
Yeah, here.
Yeah.
I just want to know how to determine the weighting factors.
Those are determined by this Gauss quadrature. So, I mean, you have that the points here, 1 over the square root of 3 and the square root of 0.6.
Yeah. I just want to know, how can we know this?
You just look it up in a table, because they are given by this Legrand polynomials. Actually, you don't need to do much in the specific codes, because it's should be given here. So here are all these points given for the different Gauss quadrature. So they are always the same, because they are roots of these specific polynomials. So there are a limited set of Gauss quadratures that are used, and they're always the same, actually.
Okay, I understand.
Okay, any other questions? Okay, so how far should you be in exercise A for next week to follow the lecture? So it's good if you can, let me open exercise A. It's difficult for me to know exactly how far you have gone, since we don't have the sort of physical lecture hours and stuff. But today's lecture covers much of what you need for part 2, the plane stress problems. So after this lecture, you should be able to work out this part and the cantilever beam. And for next week's lecture, we will start going into plate and shell elements. So now we're still in the realm of plane stress and plane strain analysis. So it's good if you are able to finish up until this point until next week. I know from previous years that most of you will be a little bit stressed up about falling behind in the exercises, and you may not have finished all of this until next week. But that's still okay, because you have time until the exam to finish all this. But until it's good if you skim through the lectures also before Monday, so that you're prepared for that. So then we will go into plate and shell theories, or other plate theories in the first part, which is applicable to part 3 of the exercise A. Okay, any other questions so far?
Okay, so I would probably take the opportunity to ask about the exercise part, because MATLAB is, are we done with the MATLAB part when we finish, because you mentioned Abacus. I see in part 3 it says exercise should be solved using Abacus. So are we done with MATLAB?
Yes, more or less. I mean, in exercise in part 3 you will use Abacus to do the analysis, and then you will extract some results and post-process that. You can do that in just Excel or stuff, but I would prefer to do it in MATLAB. But the actual coding is done in MATLAB at that part. So then we go to using Abacus.
Okay. And then in exercise B, well, whatever comes after, there's no MATLAB in those parts either, or?
No, I think that Romain, who is responsible for the pavement engineering part, is using Abacus. He will give you some additional tutorial, I believe, on using Abacus and some inputs and stuff. And for exercise C, which hopefully will be done in Plexus, you will get some extra material related to that as well. So on the Canvas page, I have a folder here, exercise A, and they will make similar folders for exercise B and C.
Okay.
And also under exercise A, you may have seen this introduction to Abacus to get you started on that. So if you follow, I would recommend you when you start using Abacus that you follow this introduction to get familiar with the program. So then the exercises will go smoother, I believe.
Okay. Also a question, I think someone mentioned it last lecture, but how strict are you on correcting now when we maybe don't have the same opportunity to check our results and compare with others and stuff? How strict are you when it comes to the bonus points for the exam when we hand in these exercises?
Yeah, I mean, I think I will probably not be the one correcting the exams. I think Sarah, that is signed up as an assistant teacher, she said before that she will help out to correcting the quizzes and the exercises. Now we don't have any quizzes, so she will only need to do exercise A. But typically we are not super strict. The most important is that you compile the results in a report, preferably following the structure that I have in this template, to make it easier to review for us, and that you have the correct results. So if you have a few inaccurate results or mistakes somewhere, we may make notes of that, and if it's too large error, we will deduct some fraction of these points. So in total, there are 3 extra points for exercise A, and typically for every sort of significant mistake, you will have a small deduction of that point. So you will likely not end up with 3 points in total, but maybe like 2.7 or 2.3 or something like that.
Okay. Thanks.
Yeah. Yeah, I mean, we've had this course running for about 10 years or so, and I think every year in the course evaluation, people think it's a rather demanding course that needs rather large attention. So you need to put in typically many hours in the exercises, and even more so, I believe, when you are doing this remotely at home. Because
it's really difficult, actually. It's
it's easy to get stuck on things.
Yeah, especially when you sit by yourself and try to figure it out. So at least I think it's pretty demanding. So
yeah. So we will try the best to make the assistant teaching work in the afternoon session, but also we promote you to collaborate with each other. I mean, you're supposed to work in groups of 2 people. Some exceptions have been made with 3 people in groups for different reasons. You can also solve it individually by yourself if you like, but it will be a little bit more demanding, obviously. But still, you can contact each other to ask questions and try to help each other out. So yeah, it may get a little bit stressed if you get stuck on the very first part of the exercises, and then you see that there's a lot of things to be done here. But and I mean, mathematically speaking, the mathematics in this course, yeah, it's fairly theoretical, but it's not extremely theoretical. It's more that the concept as a whole is maybe a little bit new to you. So yeah, the first time you work with finite elements in this context, it takes some time, but if you put down a lot of hard work in it, it will get easier in the end.
Yeah. Okay, thanks.
Any more questions? Okay, I think we can